Assalamualaikum everyone, and today we are going to dive into the experiment 1, shape of molecules. But first, let us introduce ourselves.
My name is Muhammad Harizan Hazim bin Harizan. My matrix number is A220312.
Nama saya Nusya Suhaini binti Muhammad Syawal, bernombor matrik A2176553.
And I am Nur Syairah Nadira binti Erman, and my matrix number is A216762. Key objectives of this experiment is to write the structure of molecules and to apply basic aspect of bonding to molecules. Then, to predict and to visualize best structures of molecules. Hello everyone, today we are diving into the invisible but fascinating world of molecular geometry. The purpose of this experiment is straightforward. We want to bridge the gap between 2D Lewis structures on paper and the actual 3D space structures of molecules. By building physical models, we are testing a core rule of chemistry, which is electrostatic repulsion. Because electrons repel each other, bonds and lone pairs will automatically arrange themselves to be as far apart as possible. Our goal today is to map out these shapes, measure their specific bond angles, and see exactly what happens when sneaky lone pairs force bonds out of their perfect alignments. And this is the materials that we use for the experiment. Now let's move on to procedures.
Firstly, molecule having central atom with 2 electron domains. The Lewis structure of beryllium hydride was written. A model of beryllium hydride was constructed using a 2-prong beryllium atom and 2 1-prong hydrogen atom linked by 2 5cm plastic straw. The model for beryllium hydride was drawn with each atom represented by a circle containing the chemical symbol and each bond shown as a straight line. All atoms were placed in the same plane of the paper. A ruler was aligned with all 3 atoms of the beryllium hydride model. All the atoms lie approximately in a straight line and the shape is linear shape.
For part 2 of our experiment, we explored the geometry of molecules that have central atoms with 3 electron domains. We did this by building and analyzing models for boron trifluoride and tin dichloride. We started by writing the Lewis structure for boron trifluoride or BF3. Using plastic centers and 5cm straws, we constructed a physical model. We then drew the model flat on paper, specifically ignoring the lone pairs on the surrounding fluorine atoms to focus on the overall geometry. When we measured the angles between the adjacent bonds with a protector, we observed that they were all equal, because boron trifluoride has 3 bonding pairs and 0 lone pairs on the central boron atom. It forms a trigonal planar shape. The electrostatic repulsion spaces the bonds out equally, resulting in bond angles of exactly 120 degrees. We verified this spatial arrangement by running a cotton thread through the fluorine atoms, which perfectly outline a flat triangle. Next, we moved on to tin dichloride or SnCl2. After writing its Lewis structure, we modified our existing boron trifluoride model by removing 1 plastic straw from the central atom to represent a lone pair of electrons. We drew this model representing the lone pair on the central atom with a straight line ending in 2 dots. For tin dichloride, the central atom has 2 bonding pairs and 1 lone pair. Because lone pair exert a stronger electrostatic repulsion than bonding pairs, the remaining bonds are pushed slightly closer together. This gives the molecule a bend or V-shaped geometry and compresses the bond angle to less than 120 degrees, or specifically around 95 degrees. After recording this final shape, we dismantled the model.
Part 3. The model is built using a carbon atom with 4 bonds connected to 4 hydrogen atoms. This arrangement forms a 3-dimensional structure. When a thread connects all hydrogen atoms, the shape formed is tetrahedron. The bond angle between each bond is approximately 109.5 degrees. Yes, all bond angles are nearly equal. This indicates a tetrahedral shape. And history, ammonia has 3 bonds and 1 lone pair of nitrogen atom. By removing 1 bond from ethene, we obtain the ammonia bonded water H2O. By removing another bond from ammonia, the shape becomes bent or V-shape.
But for molecule having central atom with 5 electron domains, the Lewis structure for phosphorus pentafluoride was written. Model of phosphorus pentafluoride was made using a 5-prong phosphorus atom and 5 1-prong fluorine atoms linked by 5cm plastic straw. The molecular model of phosphorus pentafluoride was drawn using perspective drawing in such a way that 3 T-shaped phosphorus fluorine points lay in the plane of the paper. The 4 phosphorus fluorine bond was out of the plane of the paper pointing toward the observer, while the 3 phosphorus fluorine bond was represented as a dotted line. The largest bond angle were measured and recorded, the intermediate and the smallest bond angle were also measured and recorded, and the number of each was stated. A cotton thread was run through all of the fluorine atoms. The space shape formed by the cotton thread was recorded as trigonal bipyramidal. This model was used in procedure 4.6 below. The Lewis structure for sulfur tetrafluoride was written. First, one of the plastic straw was pulled out from 2 phosphorus fluorine bonds that lay in a straight line. The first model of sulfur tetrafluoride was drawn in perspective drawing as described in procedure 4.2 above. The plastic straw that was removed earlier was put back and one of the 3 remaining phosphorus fluorine bond was pulled out. The second model of sulfur tetrafluoride was drawn as described in procedure 4.2 above. The correct structure is first model and the molecular shape is seesaw. The Lewis structure of chlorine trifluoride was written. A molecular model for chlorine trifluoride was derived from that of sulfur tetrafluoride by pulling out one plastic straw that was the same as the one removed above. Model of chlorine trifluoride was drawn in perspective drawing, which is exactly similar to that described in procedure 4.6 above. The Lewis structure of xenon difluoride was written. A molecular model for xenon difluoride was derived from that of chlorine trifluoride by pulling out a plastic straw similar to that removed above. The model of xenon difluoride was drawn in perspective drawing as described in procedure 4.7 above.
5. Sulfur hexafluoride SF6. Sulfur forms 6 single bonds with fluorine atom and has no lone pair. The structure is highly symmetrical in 3 dimensions. The molecular shape is octahedral. There are 3 pairs of bonds in a straight line, which is axial pairs. The thread forms an octahedral shape. We are at F5. When one bond is removed from SF6, a lone pair is introduced. The shape becomes square pyramidal. XeF4. Now we compare 2 possible models for xenon tetrafluoride. The first model is lone pair are close, which is angle between lone pairs equal to 90 degrees, and the second model is lone pair are opposite, which is angle equal to 180 degrees. The model has less electron repulsion, so the correct model is second model, and the shape is square planar, and the angle between lone pairs is 180 degrees.
Discussion time. Let's look at our first set of molecules, categorized by the electrons domain. For central atoms with 2 domains like beryllium hydride, the electron pushed to opposite sides, creating a perfectly linear shape with a 180-degree angle. With 3 domains like boron trifluoride, we get a flat, trigonal planar shape with 120-degree angles. But notice tin dichloride. When one of those bonds is replaced by a lone pair, the lone pair pushes harder on the remaining bonds, bending the molecule and squeezing the angle to less than 120 degrees. We see this exact same distortion in 4-domain molecules. The 10 is a perfect tetrahedron at 109.5 degrees, but replace one bond with a lone pair to get ammonia, and the shape becomes a trigonal pyramid. Replace 2 bonds for water, and the shape becomes heavily bent, compressing the angles even further. Now, things get really interesting at 5 and 6 domains. In 5 domains like phosphorus and fluoride, we have 2 distinct positions: axial, top and bottom, and equatorial, around the middle. When we introduce lone pairs here, like in sulfur tetrafluoride, chlorine trifluoride, or xenon difluoride, those lone pairs always fill the equatorial spots. Why? Because the equatorial plane offers more space, which minimizes repulsion. This clever positioning gives us unique shapes like the seesaw, T-shape, and a return to linear. Finally, with 6 domains, we start with a perfect octahedron at 90 degrees, like sulfur hexafluoride. As we add lone pairs, they position themselves exactly opposite to each other to avoid contact, leaving us with square pyramidal and square planar shapes. To conclude, our experiment successfully demonstrates that a molecular geometry is rarely a random accident. It is heavily dictated by the number of electron domains. While bonding pairs gives us a perfect geometries, it's the lone pairs that truly run the show, because they exert a stronger electrostatic repulsion. They bend molecules, compress bond angles, and force molecules into specific spatial orientation to maintain stability. Thank you.